Thank you, Bahong. Thank all the audience for being here. Today I will talk about the thermomechanics and particle fusion modeling of the Vitrimers. So before I talk about the Vitrimers, I will introduce what is a covalent adaptable network. So traditionally, the polymers can be classified into the thermosets and the thermoplastics. The thermosets are network materials cross-linked by the covalent bonds, and they show good structural stabilities. But the cross-links limited the material to be reprocessed or reshaped once synthesized. The thermoplastic are composed of the linear polymer chains. It can be easily reprocessed, repaired, or recycled, but the structural stability of thermoplastics cannot compete with that of thermosets. So the covalent adaptable network, the same material, is a new class of polymer that combines the structural stability of thermosets and the reprocessability of the thermoplastics. Such novel behavior are enabled by the dynamic bonds functionalized into the network. The dynamic bonds can continuously break and reform and results in the topology, the evolution of the topology. The bond exchange reaction is a typical class of dynamic reactions. It can be triggered by different stimuli, the light or heat. In a BR, a free unit will get close to a linked bond and form an intermediate group, which can then break into a new unit and a new bond. In this process, the microscopic network is rearranged and the cross-link density is preserved. The repeated BRs will allow the network to flow macroscopically, but without impairing the structural integrity. So many different CM materials have been developed. In 2011, the Labeler group have developed a CM material based on the thermally induced BRs. The Vitrimer has shown the capabilities of reprocessing, repairing, and recycling. For example, through a simple thermoforming process, a Vitrimer strip can be permanently reshaped. And for the repairing, the two Vitrimer strips can be welded together under the heating. The Vitrimer can also be recycled. The broken parts of the Vitrimer can be recycled to the new parts through injection molding. We, in 2014, have also demonstrated the Vitrimer can be recycled from the powder through a heat press process. So in above applications, there are two fundamental behaviors, the bulk stress relaxation behavior and the interfacial healing behavior. The two behaviors enable the capability of particle consolidation and fusion under the heat press, which is a fundamental process underlying this powder-based recycling. So our work is to understand and model these material behaviors. We will first focus on the bulk material behavior, the thermomechanics of the Vitrimer, and then using the interfacial heating model developed by Yu, we will study the consolidation and fusion of the Vitrimer particles under the heat press. So for the bulk Vitrimer behavior, the previous studies have focused on the uniform heating case. Since the reaction kinetics are governed by the Arrhenius law, the material also exhibits Arrhenius-like temperature-dependent relaxation behavior. That is, the relaxation time scales with the exponential of 1 over temperature T. Long in 2013 developed a constitutive model for the Vitrimer, which can capture the experimental behavior of the Vitrimers. However, For the non-uniform or the local heating, the complex coupling between the mechanical deformation, heat conduction, and the chemical reactions can be more complex. The heat conduction causes evolving temperature field. This can lead to the evolving deformation field in three aspects: the BR-induced stress relaxation, the thermal expansion, and the modulus change due to the entropic elasticity. So we will focus on studying the coupling between the thermal and mechanical, and study the thermoforming process. So first, I will introduce the constitutive model developed by Long. So consider a material point subject to the thermal and mechanical loading. The chains within this point can exchange through the BR. A basic assumption for BR is that the stress carried by a reacting chain will be relaxed after the BR, and the new polymer chain is born at a stress-free state, and it will start to accumulate deformation since its reforming state. So to obtain the total stress of this material point, we need to track the evolution of the chain composition, that is the original polymer chains and the reformed chains born at different time. So the total for the original chains, it experienced deformation from the original from the time zero to the current time t, and the reformed chains born at time tau will experience the deformation from tau to t. So we can sum up the stress of different chain groups and obtain this form for the Cauchy stress. And for the evolution of the chain composition, they are governed by the reaction kinetics, that is Arrhenius law. So the chain densities are dependent on the temperature. The temperature field is governed by the heat conduction law. So after implementing those model in the user material subroutine, we are able to simulate the material behaviors. So the previous studies, first we consider the thermoforming based on the twisting. The previous study have focused on the uniform heating case. So the Vitrimer strip shows the uniformly distributed shape after the processing. If the heating is applied to a local region, the stress relaxation is coupled to the heat conduction, which can be described by the two-dimensional parameters, the YR and YC. The lower YR implies the higher stress relaxation extent, and the lower YC represents the faster heat conduction. For the uniform heating, the YR is sufficient to describe the relaxation and shape fixity effects. But for the local heating, the three cases shown here have the same YR but with different YC. For the high temperature and short time case, the YC is high and implies a relatively slow heat conduction. So the relaxation effect is confined in the heating region. For the low temperature and a long time, the YC is low and represents faster heat conduction. So the whole strip exhibits the relaxation effects. There is another example for the thermal imprinting. We use a high temperature rigid indenter to press a low temperature Vitrimer substrate and hold the indenter for time TE and unload. The heat can be conducted from the indenter to the substrate and induce the stress relaxation. So an imprint can be finally obtained. When the heat conduction is relatively slow, that is the high temperature and the low and the short time was used, the high temperature will be confined to the region near the contact interface, Then the localized stress relaxation can cause the material in this region to be compressed more. And then it will creep up due to the Poisson's effect. And finally forming the final imprint significantly deviating from the initially deformed profile. If we use a much lower temperature but long heating time, the final profile can be very, look at this blue line. The heat conduction is relatively fast, so the final imprint can be very close to the initially deformed profile. So this is for the bulk thermo-mechanical behavior of the Vitrimer. So now we go to the particle fusion. So this is motivated by the two questions. In the application of the Vitrimer recycling, the different pressure as shown by different lines and the different heating time can lead to the material with different elastic modulus. And in our recent work, we have demonstrated the rapid fabrication of the fiber reinforced Vitrimer composites based on heat pressing the polymer powder and the carbon fiber mat. We also see that the temperature, the pressure, and the heating and the processing time can significantly affect the fusion quality of the Vitrimer matrix. So how the processing condition affect the fusion process is the first question. Also, the Vitrimer powder shows a very random particle size. How the particle size affects the fusion process is the second question we want to answer. So we will build the finite element model for the problem, and the two-dimensional case is considered here. For the mechanical process, the random particle packing, the finite deformation, and the interparticle contact will be considered. Also, the bond exchange reaction induced stress relaxation and interface healing will be modeled. So this is a simulation procedure. We first put the particles into a box and to shake the box to obtain initial dense packing for the particles. And then we use this packing as a geometry of the finite element model and perform the heat press simulation. During the heat press, the interface healing between the contacting particles can bond the discrete particles into a fused continuum. And the extent of the interface healing is governed by the density of the molecular bonds established across the interface due to the BERs. Here we use the cohesive zone model to describe the field interface, and the parameters depend on the interfacial chain density due to the healing. To determine the interfacial healing chain density, we refer to the interfacial healing model developed by in their model, the time evolution of the chain density at the interface is described by the diffusion of the polymer chains. Look at this diffusion equation. The chain density eta is a function of position and time. And TR is a characteristic relaxation time of the Vitrimer. It's dependent on the temperature T. At the beginning of the healing, the chain density distribution is represented by the blue line. The chain density is 0 inside the gap, the interface gap, and is a constant N0 outside this gap. Solving this equation using these boundary conditions, we can obtain the chain density, the interfacial chain density in this formula. From the formula, we can see with the longer healing time T or the smaller TR, which corresponds to a higher temperature, the interfacial chain density is larger. The pressure does not appear here, but in practice, the pressure may also affect the healing if the surface roughness is considered. Note that the derivation of this formula have assumed the molecular scale contact between the two surfaces. While the Surface roughness can prevent the uniform contact between the two surfaces and results in a smaller real contact area A than the nominal contact area A0. So to consider this effect, you have used the Pearson's model to describe the area evolution and obtain this integral form for the average chain density. Here the dA is increased the interface area during the time ds, and this incremental area experienced the healing from time s to time t. So this formula has summed up the chain densities contributed from all the different incremental areas in the time history. And in the macro scale, during the heat press, the nominal contact area A0 can also evolve. So to consider this effect, we use a similar strategy and obtain this average the chain density for each contact interface between the particles. And once we have the chain density at the interface, we can determine the cohesive zone model. Then we can simulate the unit tension process. Here we can extract the effective stress strain curves and calculate the modulus and the strength from the curve. We can see the particle system have been broken. So first, using the model, we study the effects of the particle size. We consider 3 cases with different particle size. For the heat press step, the 3 cases show slightly difference in the time in the porosity evolution. So from the uniaxial tension step, we obtain the modulus and the tensile strength. They show no significant difference in the modulus. Such insensitivity can be simply explained by the rule of mixture that the effective modulus scales with 1 minus porosity phi. Since the phi is on the order of 0.1, so the effective modulus is not sensitive to its change. However, the strengths show much difference among the 3 cases. To understand this, we plot the probability distribution of the interfacial chain densities. On the right-hand side is a snapshot. Example case. For each interface, an interfacial chain density can be calculated from the healing model. If we extract all the interfacial chain density for all the interfaces, we can plot their probability distributions for the 3 size cases. And the results show that the median degree of the healing cannot, they show a similar median chain density. So the median degree of healing cannot explain the difference in the strength. But the variation in this chain density can explain it. For the smaller particles, the interfacial chain density is more concentrated to the median value, meaning the most interfaces have the similar healing extent, and there are few weak interfaces. While for the larger particles cases, the chain density is more randomly distributed in a wide range, and meaning there are more weak interfaces that can facilitate the structure failure and lower the strength. So therefore, the strength is governed by the uniformness of the interfacial healing degree when the medium is similar. So now we study the particle size variation effect. We consider the non-uniform particle size in 5 different cases with the same average cases are used. The first 4 size groups follow the normal distribution with different standard deviations. The 5th group uses the 2 distinct particle sizes. On the right-hand side, we show the porosity evolution for the 5 cases. And we see that the particles with the mixed size show lower porosity than the equally sized particles. implying the better consolidation. And also from the comparison of mechanical properties, we again see the particles with mixed size can achieve a higher strength after the fusion. So here is the effects of the processing conditions. We obtain the general trend inconsistent with the experiments that the longer healing time, the higher pressure and higher temperature can lead to sample with higher modulus. So here is a summary. In the first part, we developed the finite element models, that is thermo-mechanical behavior of the Vitrimer under the non-uniform temperature field. And in the second work, we developed a model to study the consolidation and fusion of Vitrimer under the heat press. I would like to thank my co-authors and any questions from the audience.
Okay, thank you, Xiaohao. Let's see. Professor Gao has a question.
Hey, very nice work. So I think I finally understood some of your work. So I heard Ronglong's talk before, couldn't understand. So now I have a better understanding. Very nice work. I just have one confusion about your early talk on this forming. In one of your phenomenon simulations, you showed this indentation, two spheres, and then the material in between got squeezed a little bit earlier than this. Yeah, so my general question is, I mean, I don't know much about the softer material, but when people work on metals, when they try to do this kind of thermoplastic imprinting for metals, so you would hope that at a very high temperature, the metallic materials would flow very easily and do and follow whatever your imprinter's shape. But the reality is often the failure is very common. So the metallic materials would fail, and when you squeeze it, you actually chip the material, right? You kind of this is like it's more like you squeeze it, then it got fractured off the rest of the material. Even this is at a high temperature. And sometimes even you can have the printed the shape, and the strength is very poor. So you already damaged the material. We can certainly understand that in metals, they probably do not prefer this kind of large deformation. Now, throughout your talk, so I was wondering, this is more like my own limited knowledge on this topic. Don't you guys also have this damage or failure problem? So what governs this failure? Maybe the failure strength is too large that you don't need to worry about it. And but here on this plot, the nominal strain is 1.42. This is huge, right? So, well, would you fail the material eventually?
Thank you for the question. So for the Vitrimer, so firstly, it's different from the metal. The viscosity comes from the different mechanisms. But for a question, I would think it may fail, because we have not done the experiments on this problem. But from my experience, when if we twist or bend a Vitrimer strip, and when we apply a local heat, the local heat will induce the local stress relaxation, and to keep the force equilibrium, the local stress relaxation can cause the material to deform more. If I bend it, it can bend more in this local region. So usually we will see the crack in the material for the Vitrimer. So I think like the nominal strain is very large, so it should break if we do the similar things in the experiments.
Yeah.
And this is my understanding.
Thank you. Mm-hmm.
So what? So I don't know about this. But why do people use particles to do this thermal imprinting for Vitrum?
Oh, you mean for this thermal imprinting? Actually, I don't know. I'm guessing it's just so if you want to make a print, usually people may use a mold to, like for some thermoplastic, it can at high temperature it can become a fluid, it can flow, and to in a mold to make it. Here, if you use like an indenter to press it, it's like a thermoforming process. So no mold is required, and the complex shape can be made through this kind of the method. We just apply the deformation to apply the heat to fix the deformation and then release the load. So I think it can be a good method for the application.
So does people also make a large piece of Vitrum just by polymerization?
Sorry, you mean make large piece of by adhesion?
By polymerization.
Oh. Actually, the Vitrimer, the main application for the Vitrimer should be in the composite field, since it's a good, because this material is thermoset, it's a cross-linked material, but it can be reprocessed and recycled. So it has a very good potential being used in the to make the composites, since usually the composites are made of the thermoset material, and once synthesized, it cannot be reprocessed and recycled. So this will lead to severe economic and environmental problems. So the main application for such material should be in the composite material.
Okay. So I guess the thermal imprinting is used for recycle the material, right? So, okay.
It's just a demonstration for the local heating effect, the coupling between the heat conduction and the stress relaxation.
Any other questions? Okay, so the time is already 2 minutes, so we can move on. Let's thank to our speaker and move on to the next one.